Welcome to the Problems Channel Season 2, Episode 9, the episode in which we will discuss the solution of the mathematical problem S2M11. Before we do that, however, as a friendly traditional reminder, if you're joining our channel mid-season, then it is a good idea to go to the home page of this channel and in the channel's trailer section find the episode titled The Problems Channel How To, and watch that episode in its entirety, because in that episode we explain and motivate everything that we do on this channel. The thumbnail and the title of this episode should read Odd Colony of Infinitely Excitable Cells, because in the mathematics problem S2M11 we're given 9 nerve cells that are sprinkled uniformly over the periphery of a circle, and each and every such cell can be in only one of only two mutually exclusive states: excited state and not excited state. We're told that in this colony of nerve cells, precisely 4 cells are in the excited state and precisely 5 cells are in the not excited state. For demonstration purposes, we will designate cells that are in the excited state with a red or pink solid circle as shown over here, depending on how this color renders on your monitor. And we will designate the cells that are in the not excited state with a hollow circle as shown here, 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 and here, for example. We're also told that a specific permutation or a specific mutual juxtaposition of the given cells on the periphery of the parent circle does not matter apparently. We know that if a cell is in the excited state, as shown over here, for example, this cell emits 2 signals over both of its circular arcs, to its left and to its right, if we agree to designate the direction that is left and that is right with respect to the center of the parent circle. For example, if we put the center of the circle over here, then for this specific cell, the left will be this direction and the right will be this direction. A cell can become excited if and only if it receives precisely one excitement signal from one of its immediate left neighbor and not the right one, or precisely from one right immediate neighbor and not the left one. In other words, a cell can become excited if and only if it receives precisely one signal from one side and not from the other. Moreover, we know that if a given cell, whether it is excited or not excited, receives a signal from both sides, then we agree that these signals cancel each other out, and that specific cell percolates into the next state of the time evolution of this colony in the not excited state. Also, in this problem, we operate in terms of classical physics, so to speak, because we agree that the signals that are emitted by an excited cell reach both of its immediate neighbors simultaneously at one and the same unit of time, let's say t and t. That unit of time doesn't really matter. It can be nanoseconds, microseconds, milliseconds, 1 second, 1 minute, 1 hour, whatever, it doesn't matter. We'll refer to it as one unit of time. For the purposes of the question that is posed by this problem, we'll agree that the entire colony of cells is in the excited state if in that colony, at that particular moment of time, there exists at least one cell that is in the excited state. And likewise, we'll agree that the entire colony of cells is in the not excited state if all of its cells are in the not excited state. Consequently, the question of the mathematics problem S2M11 is the following. if this specific colony of nerve cells is left to its own devices. In other words, if this specific colony of 9 cells operates under an infinite time model, then will that colony remain in the excited state indefinitely, or in a finite amount of time, this colony will percolate into the not excited state? Right now, we're studying the mechanics of the reverse order problem solving approach, and precisely because of the physical placement of this problem in the sequence of problems that we solve on this channel, it is evidence that somehow, somewhere, the reverse order problem solving approach will come into the process of searching for a solution of this problem. However, psychologically, when we set our eyes upon a problem statement such as this one, our natural reaction is to investigate and try to understand the basic behavior of, for example, the colony of cells, starting with a very small number of cells and gradually working our way up to a larger and larger number of cells. To that end, we begin the study of the time evolution of this type of colony of cells with precisely one cell. Before we begin our analysis, we keep in mind two things. One, mathematics is an art. Mathematics is an art of telling a story. Mathematics is an art of telling a story of how and why, and as the potential authors of such a story, we're on the hook to demonstrate and exhibit creativity, ingenuity, and improvisational skills. And two, mathematics is not about good grades. Mathematics is not about passing an exam. Mathematics is not about taking and passing a quiz, because mathematics is about a true, deep, genuine, natural, and perhaps even synthetic understanding of the material at hand. And such a level of understanding is developed only through a concentrated effort and is never easy or quick. As such, in this specific case, it should be evident that if a colony of cells given in this problem consists of precisely one cell, then if initially this cell is in the not excited state, which we depict here with a hollow circle, then it should be evident that there is absolutely no hope for such a colony to transition from not excited to an excited state. And in a somewhat highbrow mathematical vocabulary, we will say that for any, and this is a symbol for any, for each, and for all, for any whole positive number n, such as 1, 2, 3, 4, 5, and so on. If we look at such a colony at a moment of time equal to n times t, where we remember that uppercase T designates the time which it takes for the excitement signal to reach the immediate neighbor of the signal emitting cell, then such a colony will always be in a not excited state. Consequently, from now on, as we analyze colonies that consist of more and more cells, we will not be looking at this specific case, because it should be clear that once such a colony is not excited, then it will remain not excited indefinitely. Now let's take a look at the case where initially our single cell is in the excited state, as depicted with this solid red or pink circle. And we know that according to the problem statement, such a cell will emit two signals, a signal to its left in this direction and the signal to its right in this direction. And from now on, we agree that we establish the direction left and right with respect to the center of the parent circle. In other words, if we're standing on the periphery of the parent circle and looking at the center of that circle, that direction of our gaze determines the left and the right. We also know that these signals will travel along the parent circle at the same speed and at the same time. They will do what? Well, the signal that this cell emits on its left side will travel around the circle all the way and arrive at the cell from its right, and the signal that this cell emitted from its right direction will also travel around the circle, and it will reach this cell from its left at exactly the same time, and that time will be t in our designation. And it should be evident that because this cell will receive the incoming signals from both directions at the same time, these two signals cancel each other out, and into the next state in 1 unit of time t, this cell will percolate or will transition as not excited. And as we analyze this case previously, we understand that in this specific scenario, in 1 unit of time t, our colony of cells will transition from the excited into the not excited state, and it will remain there indefinitely. Now that we analyze the behavior of the colony of cells that consists of one cell, we will move on to the analysis of the evolution in time of a colony of cells that consists of precisely two cells. When our colony of cells consists of only two cells, then we begin our analysis with the case when in such a colony only one cell initially is in the excited state, as depicted with a solid red or pink circle over here. What will happen then? Well, by the problem statement, we know that such a cell will issue an excitement signal towards its right, this way, and towards its left, this way. Again, we agree that when this cell sits at the periphery of the parent circle and looks inside the circle at its center, then that direction of its gaze establishes the right and the left. We're also told that in one at the same time, from the classical physics standpoint, that unit of time will be t over here and t over here. This signal will reach its immediate right neighbor, which is this cell, and its immediate left neighbor, which is one and the same cell. And we know that when a particular cell receives an excitement signal from two directions, like so, it transitions into the next state not excited. So we can write this down already like so. This cell becomes not excited. Also, this specific cell that emitted the excitement signals over the parent circle does not receive an excitement signal from one specific direction at all. Actually, no signals come to this cell because the first immediate neighbor on either side of the signal emitting cell consumes that signal completely in its entirety and prohibits or prevents the further propagation of the signal over the parent circle. Consequently, in 1 unit of time, we'll designate it with arrow like so, in 1 unit of time, the originally excited cell becomes not excited, like so. And we see that this colony of cells in 1 unit of time transitions from an excited state into not excited state. And as we discussed in the previous segment, that colony of cells will remain in the not excited state indefinitely, which is more pedantically or more precisely means that for any whole positive number n, such as 1, 2, 3, 4, and so on, if we care to look at that colony n times t units of time later, that colony will always be in the not excited state. Awesome. What will happen? Let us analyze the case when both of the cells that make up this colony are in the excited state. We'll depict these cells with a solid circle like so, and we will analyze what will happen in this case also. Well, it's not that difficult to see that according to the problem statement, both of these cells, each of which is in the excited state, will emit an excitement signal in both of its corresponding directions. This cell will issue the signals like so, and this cell will issue the signals like so. Again, in one at the same unit of time, 4 events will happen. For example, this signal will reach this cell in the unit of time t. This signal will reach this cell in the unit of time t. The signals, when they meet, they pass through each other. And at the same time, this signal will reach this cell, and this signal right here will reach this cell also in this one and the same unit of time t. According to the problem statement, whether a given cell is in the excited state or not excited state, when such a cell receives a signal from both of its sides, then these two signals cancel each other out, and such a cell percolates or transitions into the next state of the time evolution of such a colony in the not excited state. Consequently, here we also realize that in one unit of time, depicted like so, in one unit of time, t, our colony of two cells transitions into the not excited state, and it will remain in that state indefinitely. Now that we have a reasonable understanding of the time evolution of a colony of two cells, we will look at the time evolution of a colony of 3 cells. It is natural to begin the analysis of the time evolution of a colony of 3 cells with only one cell being in the initial excited state as depicted over here. In this specific scenario, how will the time evolution of this colony progress? Well, we know that the moment this cell becomes excited, it issues or emits 2 signals, one in this direction and one in this direction. And we know that in exactly the same unit of time, again, t over here and t over here, both of these signals will reach their effective left and right neighbors with respect to the signal emitting cell at the same time and simultaneously. And because, for example, this cell will receive precisely one signal from its left and nothing will come from its right, because this cell will consume this signal completely and in its entirety, and it will prevent the propagation of this signal further over the parent circle. And by the rules given in the problem statement, that means that this specific cell will percolate into the next state by being precisely excited, as shown over here. Likewise, this specific cell will receive the excitement signal precisely from its right and not from its left, because this cell already consumed the signal traveling in this direction over the parent circle. And that, again, by our earlier given definition, means that this cell will percolate into the next state also in the excited state, like so, and we just have to analyze the time evolution of the signal emitting cell. Well, again, because these two cells consumed the signals, the corresponding signals completely and in its entirety, and they prevented the propagation of these signals over the parent circle any further, this cell will not receive any signals at all, and that means that it will percolate into the next transition in the state that is not excited, like so. We'll depict it with a hollow circle, and that means that in 1 unit of time t, this is our first transition from the initially excited state, because in this colony of 3 cells, 1 cell is in the excited state. Consequently, the entire colony is excited. And over here we have 2 cells in the excited state, and the colony is excited as well. What will happen next? Well, let us analyze the time evolution of this configuration. We know that, for example, let's work with this cell. This cell will issue an excitement signal in this direction and in this direction. This cell will issue an excitement signal in this direction and in this direction. And we know, again, by the classical mechanics principle, the notion of simultaneity exists and makes sense, unlike in the Einsteinian or relativity case. And in 1 unit of time t, these 2 signals will come into this cell right here, and we know that in this case these 2 signals cancel each other out, and this cell percolates into the next transition in the not excited state, like so. And what about the signal emitting cells themselves? Well, the signals over here on the bottom arc of the parent circle will travel through each other, and this signal will come into here. Let me depict it with the pink color here. And this signal will come into the cell right here precisely, which means that, for example, this cell will receive the signal from only one of its neighbors, from the right neighbor, and no signal from the left neighbor, which means that this cell will percolate into the next transition in the excited state. It will be excited, like so. And likewise, this specific cell, it will receive the excitement signal from its left, but no excitement signal from its right. And by the rules established in the problem statement, that cell will also percolate into the next transition of this colony in the excited state. And what type of conclusion can we draw from this experiment? Well, we see that these 2 configurations right here, this one and this one, are actually identical, and that means that on the next beat, so to speak, or t units of time later, this configuration will be taken back into itself, which means that in just 1 unit of time t, our colony went from this configuration, where initially only 1 cell is excited, into this configuration where 2 cells are excited, and again, indefinitely, this colony of cells will remain in the excited state forever and ever, always. Any unit of time t, any positive multiple unit of time t we care to look at the system, it will be eventually in this state, and it will never escape from this state. And because in this case there are 2 excited cells in this colony will remain excited forever and ever. And we can even say that under the time tending to positive infinity here, the system will be in the state that is excited, and we can maybe already draw some conclusions. Now that we understand the behavior of the colony that consists of 3 cells, we'll take a look at the colony that consists of 4 cells. As we begin our analysis of a colony of cells that consist of 4 cells, as shown over here, for example, we begin to realize that it's not just the number of excited cells, but their permutation or mutual juxtaposition on the parent circle that may make a lot of difference and be important. In the configuration shown, what will happen next? Well, we already know that, for example, let's work with this cell. This cell will emit an excitement signal this way and this way. And this specific cell that is in the excited state will emit a signal this way and this way. We already understand that in one and the same unit of time t, here, here, and here, what will happen? The signal that is emitted by this cell in its right direction this way will reach this cell, and this cell will consume that signal completely and in its entirety. And because this cell will not receive any signals from its right, because this cell will consume this excitement signal right here, by the rules established in the problem statement, this cell will percolate into the next transition in what? In the excited state, like so. We'll depict it here like so. Likewise, this specific cell will receive precisely one excitement signal from its right. It will receive no signal from its left because this cell will consume this signal in its entirety and completely and will prevent the propagation of this signal any further over the parent circle. And by the rules established in the problem statement, we know that this cell will percolate into the next transition in the excited state as well. And what about the signal emitting cells over here? Well, again, because the corresponding signals over the parent circle here below will be blocked and consumed by these two cells. For example, this cell in one and the same unit of time t will receive the signal over here from its left and nothing from its right. And this cell will receive the excitement signal from its right, but nothing from its left, and it will percolate into the next transition of this colony in the excited state as well. Consequently, this cell will be excited, this cell will be excited as well, and that means that this is the new configuration of our system in one beat or in one unit of time. This is the transition of our 4 colony of cells from here to here. What will happen next? Well, by now we already see what is going on. We are in a good position to understand what will transpire. In this case, all 4 cells will issue their respective exciting or excitement signals this way, this way, this way, this way, and this way. And due to the rules of propagation of the signals that we already explained, it is evident that, for example, going counterclockwise and starting with this 1 o'clock cell, what will happen? This cell will receive the excitement signal from this direction and from this direction, and these two signals will cancel each other out, and this cell will percolate into the next transition, being in what state? Not excited. This, by the looks of it, 10:30 or 11 o'clock cell will receive an excitement signal from this cell from this direction and from this cell from this direction. These two signals will cancel each other out. Consequently, this cell will percolate into the next state, not excited. And by symmetry, the same thing already will happen over here, we understand, but let's just discuss it shortly. This cell will receive the excitement signal from this cell from the right and from this cell from the left, and these two signals will cancel each other out, making this cell not excited. And likewise, this cell will receive an excitement signal from this cell from its right and from this cell from its left. These two signals will cancel each other out, and this cell will be not excited. And this will be our final, so to speak, configuration. And we see that in this case, in 2 units of time, our system or our colony of 4 cells where 2 immediately adjacent cells were initially excited transitioned into the state that is no longer excited, because as the colony, no single cell in this colony is excited. And we next may want to analyze the case, for example, where we also have precisely two excited cells, but which are diametrically opposite of each other. In other words, 2 excited cells are broken up, so to speak, by the not excited cells. Let's say we do it over here. If one cell is excited here and the other one is excited over here, this cell is not excited and this cell is not excited, then it should be already evident that in 1 unit of time t, what will happen? Well, for example, this cell will emit the signal this way, and this cell will emit the signal this way and this way. And what will happen? Well, these two signals will collide at this cell over here. This cell will consume both signals in its entirety, and these signals will cancel each other out. So this cell, for example, will still be not excited. Likewise, by symmetry, this cell over here, it will receive the signals from its immediate right neighbor and immediate left neighbor. These signals will cancel each other out, and this cell will percolate into the next transition, not excited. Likewise, because these two cells consume the incoming signals completely and in their entirety and prevent the propagation of the signal over the parent circle any further, this excited cell and this excited cell will not receive any signals whatsoever, and into the next transition they will go also not excited like so. And in some sense we can see that we basically have the same configuration over here. And perhaps the last interesting, or one of the last interesting cases, is when we have precisely one excited state. I'll show it over here, and the other cells are not excited, as shown over here, like so. If we have it this way, then what will happen in this case? Well, in this case we see that, for example, this cell will issue the signal this way and this way. That cell itself will not receive any signals. It will become not excited in the next transition. These two signals will excite these two cells. This cell will be not excited, and we will obtain this configuration right here. I'll mark it over here in 1 unit of time t. This configuration will percolate into this one, and this configuration will percolate into this one. So either way, it looks like our colony of 4 cells will become not excited in a finite amount of time and will remain not excited indefinitely. One of the cases that you may want to investigate on your own, I'll use which space, maybe right here, when we have precisely 1, 2, and let's say 3 excited cells and 1 cell precisely is not excited, for example, this way, what will happen then? Well, we already understand that, for example, this cell will emit the signal this way, and it will emit the signal. This cell will emit the signal this way. So this cell will be not excited anymore. This cell will receive the signal from here, and this cell will receive the signal from this one. And what about this cell? This cell will receive the signals from here, and it will remain not excited. And what will happen then? Well, in this case, in 1 unit of time, by the looks of it, we again transition into this state where the lower right cell is not excited. These two cells over here at 1 o'clock and 8 o'clock are excited, and this cell right here, this cell, is not excited as well. In other words, by the looks of it, no matter which initial configuration of excited cell we pick for a colony that consists of precisely 4 cells, we go into the state that is not excited, and after our 4 colony reaches that state, again, symbolically, we can say that under the time tending to positive infinity, this system will remain not excited. And because 4 is what? 4 is a perfect square on one hand, and 4 is also a perfect power of 2, so it may be a little bit too early to make any sort of conclusions at this point. Next, let us take a relatively brief look at a colony that consists of precisely 5 cells. We will begin the analysis of the time evolution of a 5 colony of cells with the configuration when just 2 immediately adjacent cells are in the excited state, as shown over here. In the previous segments, I went over the mechanics of the time evolution of our cells very slowly and very thoroughly, so this time I'll step a little faster. In this case, in 1 unit of time t, it is evident that, for example, this excited cell will turn this cell on, and this excited cell will turn this cell on. This cell over here will receive no signals whatsoever, and it will remain not excited. And these two cells, by the virtue of the fact that these cells will consume the corresponding signals in their entirety, they will keep each other excited, which means that in the first transition, our configuration of 5 cells will look as follows. The top cell will be not excited. These 2 cells will be excited, and the bottom 2 cells will be excited as well, like so. And let us pretend that these cells are sprinkled uniformly over the parent circle, like so. And now we want to see what will happen in the next transition of the system. Again, we see that the top cell will receive the excitement signals from both sides, and it will percolate into the next transition without getting excited. Again, these two cells will receive the corresponding signals only from one side, from here in this direction, and from here in this direction, nothing from the opposite direction, which means that into the next transition they will go excited as shown here. And what about the bottom cells over here? Well, we see that, for example, this cell will receive an excitement signal from this cell in this direction and from this cell in this direction. And these two signals will cancel each other out, and this cell will percolate into the next transition not excited. And likewise, by symmetry, for example, this cell right here, it will receive the excitement signal from this cell and from this cell. These two signals will cancel each other out. This cell will become not excited like so. This will be our next configuration, and we already understand what will happen on the next beat. Again, our topmost cell over here, 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 and here will again keep receiving the signals from both sides, and it will remain not excited. It will be in the not excited state. The cells over here that are excited themselves, they will only issue signals in the corresponding directions, but they themselves will not receive any signals. The signals for these two cells will not be coming from anywhere, so these guys will be turned off and will not be excited anymore. And what about the bottom two cells? Well, this cell will receive the signal only from its left, but nothing from its right, and it will become consequently precisely excited. And this cell right here will receive an excitement signal from its right and nothing from its left, and it will become excited again like so. So what do we see? We see that in just how many? Let us count together. 1, 2, 3. In 3 units of time, in other words, with the period 3t, our 5 colony of cells, in which 2 immediately adjacent cells are excited and the remaining cells are not excited, will percolate into its original configuration. And that means that from this point on, forever and ever, for as long as we care to look at the time evolution of this 5 colony, it will flip-flop through the states shown over here. And in this case, in this specific configuration, it will never be in the not excited state, and it will always be in the excited state, and so on. As another sample configuration that you should investigate on your own, for example, also if we have just 2 excited state cells that are separated by 1 not excited cell, let us see what will happen. 1 not excited cell, another excited, and these 2 guys not excited. What will happen in this transition? For example, let's see, this cell is excited and this cell is excited. What will happen in this case? Well, we see that this cell right here will receive the signals from both sides, and it will become will transition into the next state, not excited. This cell right here will not receive signals from anywhere, and this cell also will not receive any signals from anywhere. So this guy becomes not excited, this guy becomes not excited. And what about these 2 cells? Well, this cell will receive the signal from here, from this direction, and this cell will receive the signal from this direction only, nothing from the remaining directions, which means that this cell and this cell will become excited, This transition will take place in 1 unit of time t. And what do we see? When we compare this configuration with, for example, this configuration or this configuration, we see that these configurations are essentially the same, or the same up to a rotation of the plane. For example, if we rotate this configuration this way or that way, we'll arrive at this configuration. Or if we decide to rotate, for example, this configuration this way or that way, we will arrive in this configuration. In this case, mathematicians will say that these two configurations are isomorphic or essentially the same, meaning that if we do not pay attention or neglect certain details that we deem irrelevant in this specific context, then structurally these two configurations are indistinguishable and one and the same. And now that we understand the scope of work, we now realize that the challenge that lies ahead of us. We're told that we're given 4 excited cells, 5 not excited cells, and in theory, we're on the hook to possibly permute these 4 excited and 5 not excited cells over a circle in all possible ways and chase down or run down the time evolution of all these configurations. So this already is quite a bit, but when we think about it, we realize that the person or the persons who put this problem together specifically did not tell us anything about a particular permutation. And from that, what kind of conclusion do we make? The conclusion that we make from this hidden, so to speak, hint is that apparently the answer to this problem does not depend on a specific permutation of 4 excited and 5 not excited cells. And we will take advantage of that observation in the next segment. By doing all the work that we have done in the previous segments of this episode, we managed to grasp the overall combinatorial volume of work that we would have to do if we were to attack this problem head-on and in a brute force manner. Here, depending on your level of mathematical maturity, if, for example, you have studied the theory of groups long enough and deep enough, you may or may not know that when it comes to circular arrangements of indistinguishable items of different types, there exists a closed form formula, and even though that formula is not horribly complicated, it is reasonably involved, and since I do not want to waste your time explaining how this formula works, I will only mention that because the whole positive numbers 4 and 5 are co-prime, meaning that the greatest common divisor of these numbers is 1. Consequently, the number of positive divisors of 1 is just 1, and that number is 1, which means that that formula degenerates into just one summand that has the following structure. It is 1 divided by 9, the total number of items that we're given here, times the value of the Euler's totient function evaluated at n equals 1, which is 1. So we multiply this by 1 times the number that is the ratio of 2 factorials. It is the ratio of the 5 plus 9 plus 4 plus 5, 9 factorial, divided by the product of individual factorials, 4 factorial and 5 factorial. Here we see that 9 and 9 factorial in the numerator and denominator cancel out into what? They cancel out into 8 factorial, and here we have 4 factorial in the denominator times 5 factorial, and 8 factorial in the numerator and 5 factorial in the denominator cancel out into what? Into 6 times 7 times 8 over 4 factorial is 24, and we see that 6 times 8 is 48, 48 over 24 is 2, 2 times 7 is 14, so in this case the answer is 14 is the number of distinct circular arrangements of 4 indistinguishable items of type 1 or 4 cells that are in the excited state, and 5 indistinguishable items of type 2 or 5 cells that are in the not excited state. And if we were to attack this problem head-on and in a brute force manner, then first we have to spend all the time generating all 14 initial circular arrangements of our 4 plus 5, 9 cells, and then we would have to run down or analyze the time evolution of each and every one of these 14 initial arrangements, 1, 2, 3, and so on. And we will have to somehow figure out if in a finite number of steps, either one or any one of these 14 initial arrangement can actually degenerate into a not excited state, or we'll have to show that none of these 14 initial arrangements can possibly degenerate into not excited state, and they always stay in the excited state indefinitely. That is the battle plan, and this is the amount of work that we'll have to do if we attack this problem head on and in the brute force. However, it is sometimes the case that when we solve this or that mathematical problem, we have no choice but to attack a problem head on. And sometimes the amount of grunt and head on work that needs to be carried out is beyond the reach of an average human being. Sometimes the amount of this grunt work is beyond the capabilities of the modern electronic computers, and yet sometimes by getting clever, it is possible either eliminate all that grunt work completely or maybe just the bulk of it. It so happens that the mathematics problem S2M11 can actually be dealt with in a clever or perhaps out of the box way. And here we recall that because we already studied the Reinterpret and Conquer problem solving approach, we understand that the moment we study this or that problem solving approach, we can apply it to the process of solving a technical problem right away. Whenever we hear the words only one of only two, mutually exclusive, yada yada, what type of happy thought may occur to us? Whenever we hear that each and every cell can be in only one of only two mutually exclusive states, then the following happy thought may visit us at some point. What if we try to splice the binary numbers or base 2 notation into our problem? In this case, it is quite natural to correlate every cell that is in the excited state, with a binary digit of 1. And conversely, whenever in our travels we come across the binary digit of 1, to such a digit we correlate a cell that is in the excited state. Likewise, to every cell that is in the not excited state, we correlate the binary digit of 0, and conversely, whenever in our computational travels we come across a binary digit of 0, to that digit we correlate a cell that is in the not excited state. Then, using our sample 3 colony of cells, whose time evolution we already analyzed in the previous segment, we want to see what the equivalent or what is the reinterpretation of that 3 colony will be. Well, in this case, it's quite easy. We see that if we reinterpret this initial configuration of 3 cells with zeros and ones, we will have our favorite circle, 1 binary digit on top and 2 binary digits on the bottom. And now the question is, how do we model or how do we reinterpret the given time evolution process of cells faithfully? Here again, depending on your level of problem solving sophistication, you may or may not know that one popular maneuver with these numbers shown over here is the following. Somehow write new numbers on the board, erase the old ones, and keep iterating this process over and over again. So the question now is, between every pairs of numbers here, what do we write? Well, we do not know any better. We just want to experiment. So we experiment. What if between each pair of the same binary digits, we write a 1. For example, here 0 and 0 are the same, so between them we write a 1. And between each pair of distinct binary digits, we write a 0. So here, for example, the digit 1 and digit 2 are distinct. Between them we write 0. And on that side, between this pair, 1 is here, 0 is here. The digits are distinct. We write a 0. Then we, as the idea prescribes, erase the old numbers. We erase the old numbers and we keep the new ones. And we keep iterating this process again. Between every pair, we write the corresponding number, erase the old numbers, keep the new ones, and so on. And we pretend that this operation happens every t units of time, precisely the same way in which the time evolution of our cells happens over here. Now the question is, does this process reflect what happens with the time evolution of cells faithfully or not? Well, obviously the answer here is not, because remember, with our correlation, to one we correlate a cell in the excited state. So here we will have a cell in the excited state, and to every 0 we correlate a cell in the not excited state. So here, I'll write it lightly, we'll have 2 cells in the not excited state. And when we compare these two configurations, what do we see? Are they isomorphic or not? Obviously, they're not isomorphic. They're not essentially the same. They're structurally different, because even if we rotate this set of zeros and ones, let's say by pi radians counter or clockwise in the plane of the board, we will not obtain the final configuration of 3 cells shown over here, because in this case we will have here what? On the top we will have 1 cell in the excited state. Here we have 1 cell in the not excited state. And on the bottom over here, after the rotation, we'll have 2 cells in the not excited state. But here, these 2 cells must be in the excited state. So what do we do now? Well, we do the only thing we can. We declare this experiment a failure. And instead of writing a1 between every 2 numbers, that every 2 binary digits that are the same, we will write the only other choice that we have. We will write a 0. What will happen then? Let's see. 0 and 0. In this pair of binary digits, the digits are the same. We write down a 0. Between these 2 digits, which are distinct, we now write, instead of 0, we write 1. And for the remaining pair, 1, 0, 2 binary digits that are distinct, what do? We write a 1. And as the rule suggests, we erase the old numbers, keep the new ones. We pretend that all this magic happened in t units of time. We go back to our correlation, and what do we see? Well, we see that to 1 we correlate a cell in the excited state. I'll show it lightly. Here we'll have 2 cells in the excited state. Here we'll have 1 cell in the not excited state. When we compare the outputs of these 2 processes, we see what? Are they isomorphically the same? Are they isomorphic or not? The answer is, of course, yes, they are isomorphic. They're essentially or structurally the same. If we rotate, for example, this guy in the plane of the board by pi radians, or upside down, so to speak, we will have precisely the same picture over here as we have over here. This cell in the not excited state will be on top, and it will be the only one, and these 2 guys will move down here, and we will have 2 cells in the excited states in the bottom, precisely as over here. And now, what is the question of the reinterpreted problem? Well, it should be evident now that the reinterpreted problem will pose the following challenge. Given four ones, 1, 2, 3, 4, and 5 zeros, let's say 1, 2, 3, 4, and 5, given 4 ones and 5 ones sprinkled, 4 ones and 5 zeros, I'm sorry, and 5 zeros sprinkled around the periphery of the parent circle, can it so happen that if the rule that we explained over here applied to these numbers indefinitely, we will obtain precisely 9 zeros? So this is a big question. Can it so happen that in a finite amount of time we'll have precisely 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 zeros sprinkled around the periphery of the parent circle? And in order to make sure that we all understand what the rule is, we'll capture it over here. We'll write 1 if the digits on a circle are different, 1 if different, and we will write a 0 if the digits are the same. This is our rule, which we apply to an initial set of zeros and ones sprinkled around the periphery of the parent circle every t units of time by keeping the new numbers, erasing the old ones, and proceeding in that fashion. Under these conditions, will it so happen that in a finite amount of time we will obtain 9 zeros sprinkled around the periphery of the parent circle? And in order to ask questions, we precisely use the reverse order problem solving approach. Now that we know which question to ask, we answer that question using the reverse order problem solving approach as follows. We know that that approach has two main flavors, the mechanical flavor and the heuristic flavor. And in this problem, by the looks of it, we will employ the heuristic flavor. And according to that flavor, the reverse order problem solving approach prescribes that we begin searching for a solution of the current problem in reverse order from the final state of the problem. So what is the final state of this problem? Well, it is natural to understand that the final state of this problem is precisely the 9 zeros sprinkled around the periphery of the parent circle, and we take that as our initial assumption. We take it as initial assumption designated with A in the circle over here, and we reason as follows. Assume that after finite amount of time x times t, where x varies as 1, 2, 3, and so on, it so happened that we obtained 9 zeros sprinkled around the periphery of the parent circle for the first time. This is our initial point. This is our starting point. I'll depict the point over here. This is our initial point. Recall my explanation of how the reverse order problem solving approach works. Here we're invited to craft a string of if P then Q implications and work backwards in reverse order from the final state of the problem towards the initial state. If x times t is the final state of the problem, then what is the previous state of the problem? Well, it is evident that the previous state of the problem will be x minus 1t. And what type of correct implication, if P then Q, can we craft in this case? And we have to make sure that we involve the previous, or x1 minus 1, x minus 1t unit of time. Well, if all the zeros around the periphery of the circle were obtained at the moment of time xt, then on the previous iteration of this system, what can we say about the quality of the numbers that we have? Well, in order to answer that question, we go back to our rule, and we sort of roll this rule backwards as well. If all zeros are present over here, that means that all the numbers were the same. That's number one. And not only that, but none of these numbers is zero. Why? Why none of these numbers is zero? None of these numbers is zero because precisely we're seeing these zeros for the first time ever. But what type of system are we working with? We're working with a base 2 system, and that system, the alphabet of that system is what? It's only 2 digits, 1, 2 symbols, 0 and 1. Consequently, if none of the numbers sprinkled around the periphery of the parent circle at that stage can be 0, then what does it have to be? It has to be 1, precisely. They are the same and they are all ones. So here at this stage, what does our distribution looks like? 1, 2, 3, 4, 5, 6, 7, 8, 9. So we'll put it here, 9 ones. So at this stage x minus 1t, we supposed to have 9 binary digits, 1 sprinkled around the periphery of the parent circle. And remember, we depict it as one successful if p then q implication over here. Again, since we're using the reverse order problem solving approach, that approach prescribes that we keep moving backwards in time. So what state of the system was before x minus 1t state? Well, it was x minus 2 times t. And what kind of if p then q implication can we craft over here that involves the unit of time x minus 2t? Well, again, we go back to our rule, and we know that if the numbers are different, then we put 1. And in reverse order, that means that if we have a 1, that the numbers were different. That means that on the circle at the moment of time x minus 2t, I'll put the arrow over here, what should we have? Well, all numbers must be different. And such numbers come in pairs, so it has to look like this: 1, 0, 1, 0, 1, 0, 1, 0, and so on. But here is the pickle. If these numbers come in pairs, then what is the total number of such binary digits sprinkled around the periphery of the parent circle? Correct, that number must be even. So we write it down over here. That number must be even. That number must be even. And in the corresponding layer of mathematics, or in the respective course in college that you may have taken or will take, it is shown that for a fixed whole positive number n greater than 1, the intersection of any two distinct equivalence classes of integers modulo n is the empty set, which is to say that for every fixed whole positive number n greater than 1, no two distinct equivalence classes of integers modulo n intersect. In this case, it means that if a whole number is even, then it is not odd. Then it is not odd, and conversely, if a whole number is odd, then it is not even. In this situation here represents a contradiction that we obtained over here by crafting our second implication. Right here we have our contradiction, and now we roll this contradiction back this way and this way. So what type of thing can stop this roll of contradiction backwards? Well, it's only our assumption, because we now think that nowhere in our reasoning we have made a single mistake. Every if p then q implication was correct. That means that the only thing that can stop our contradiction is our assumption, and that means that our assumption was not correct. Consequently, we now obtain the answer to the reinterpreted problem, and the answer is no. Under no circumstances, under no finite number of units of time, can 9 zeros be obtained and sprinkled around the periphery of the parent circle if initially we're given 4 ones and 5 zeros, and the rule for obtaining the evolution of this system of numbers is captured over here. If we step back a little, we may realize that the magic number 9 didn't really, or the specific value of that number, as long as that number is odd, did not play any significant role. Of course, it is very significant that the number is odd, but we can generalize this result with the following theorem. We can say that if n equals 2k plus 1, in other words, if an odd number of zeros and ones with both ones and zeros present are sprinkled around the periphery of the parent circle, and the rules explained over here are applied to these numbers every t units of time, then we will never obtain all odd n equals 2k plus 1 zeros sprinkled around the periphery of the parent circle. And we can now carry the solution of the reinterpreted problem back to the homeland of the original problem. What would the result of such a solution be? Well, we now understand that overall the answer to the question posed in this problem is a resounding no. The answer is no. In this specific case, the circular colony of 9 cells, of which 4 are excited and 5 are not excited, can never degenerate into a not excited state. And in positive terms, that means that given the initial setup over here, that colony of cells will remain in the excited state indefinitely and for as long as we care to look. We know that more officially we can say that for any, and this is a so-called universal quantifier, for any, which stands for any, for all, or for each, for any number n, such as 1, 2, 3, 4, and so on. If we look at such a colony at the moment of time nt, that colony will always be in the excited state. In other words, in this specific case, in this colony, there will always be at least one cell that is in the excited state. And if we tend n to positive infinity, meaning that n grows without bound, then this represents the infinite time model, which exactly means that this colony of cells will always be in the excited state. And now hopefully it is clear why I titled this episode as an odd colony of infinitely excitable cells. And again, that should be transparent that that colony, or in that colony of cells, the excitement will never peter out and will always be present. And again, now that we understand that the specific value of this odd number 9 is not really that important, we can generalize this theorem, this problem to the same theorem, which we will state as follows. Given an odd number of excitable cells with both excited and not excited cells present under the rules of time evolution explained earlier, it will never happen that that colony of cells will degenerate into not excited state. And put differently, it means that that colony of cells will be always in the excited state and it will remain in that state indefinitely. Now that we solved the mathematics problem S2M11, before we go on to the next challenge, as an extra for experts, as an optional material, I would like to give you some food for thought by unbending the circle, so to speak, by cutting it at an arbitrary location and looking at not a circular but a linear colony of cells. For curious travelers, we recommend that you cut the circular colony of cells that was given in the problem S2M11 and stretch out that circle into a line, and imagine that these cells sit on a number line precisely at the integral positions 0, 1, 2, 3, 4, 5, and 0, -1, -2, -3, and so on. And the rules of time evolution of the excited and not excited states of these cells are precisely the same. For example, over here with 3 time evolutions, I showed a simple propagation of the wave of excitement through the linear colony of cells if initially, here we have to be careful, if initially 3 cells shown over here, 3 cells over here are in the excited state, and it is depicted over here. This is the initial state. Then 1 unit of time t later, this will be the distribution of the excited cells, because, for example, we already know that this central cell, which we may designate with a number, for example, 1, this 0 will be, this will be +1, +2, and so on. This will be -1, -2 for the x sub k coordinate, for example. But we see that this cell will be turned off. Then in the second iteration, this will be the distribution of the excited cells. In the third, after the third period of time expires or elapses, this will be the distribution of the excited cells, and so on. This is just a sample, but a real, so to speak, question in the problem is determine how many cells will be excited after t units of time elapse in the system if only 1 cell is initially excited, and try to find their locations or the x sub k coordinates. And again, remember that in season, let me write it over here, season 1, episode 2, I explained how to practice mathematics correctly. We suggest that you give that problem a fair shot and try to solve this problem on your own. If you cannot, don't listen to our solution in its entirety, but only listen for minimum viable information. And here is as a hint, if you try to solve this problem and you could not, in the big scope of things and fundamentally, this problem for counting the number of excited cells and finding their locations has a lot to do with residues, of binomial coefficients, and choose k, modulo prime number and modulo prime p. And in this specific case, when each cell can be in only one of only 2 mutually exclusive positions, the role of the prime p will be played by the first, the last, and the only even prime. So in this case, p will be 2. And we suggest that you compute the residues of the respective binomial coefficients modulo 2, and then as another hint, try to see where this is going, but then as another hint, try to place these residues on top of the Pascal's triangle and see what happens. But we are done with this problem and we will move on to the next challenge. Our next challenge, the mathematics problem S2M12, will be the last problem that we will use in order to study the mechanics of the reverse order problem solving approach. And I will say a few words about this powerful problem solving approach in the next episode. But for now, we're given a sequence x sub n of real numbers that is defined as a recurrence relation. X sub n plus 2 equals x sub n minus 1 over x n plus 1. And we're told that the initial values of the elements x sub 1 is 20 and x sub 2 is 25. And the challenge in this problem is to show that for the given sequence of real numbers defined as shown above, there exists, this is a mathematical symbol called the existential quantifier. So in this challenge, we're asked to show that there exists a whole positive number n such that the element of this sequence indexed by that number x sub n is equal to 0, and we're also asked to find the value of that number. And basically, in plain English, if a sequence of real numbers is defined as a recurrence relation as shown above, we're asked to show that there will be a zero element in that sequence, and we're asked to find the ordinal position of that element in that sequence. And in order to make sure that there is no mystery behind my choice of the initial values of the elements x sub 1 and x sub 2, I'm making this episode in the year 2025. If we cut this year in half, we will have 20 on one side, 25 on the other. This is very romantic. Consequently, we have 20 and 25, but it doesn't really matter. We can try to solve this problem under the assumption that the initial values for these two elements are known and, for example, are constants c sub 1 and c sub 2. This is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will discuss the solution of the mathematics problem S2 and 12.